Chapter 2.2 Complex Functions as Mappings. The point z in the z-plane is associated with the unique point w equal to f of z in the w-plane. We use alternative term complex mapping in place of complex function when considering the function as the correspondence between points in the z-plane and the points in the w-plane. And as a remark, we cannot draw the graph of a complex function. Well, the reason to this is that, however, if w is equal to f of z is a complex function, then both z and w lies in the complex plane. It follows that the set of all points z of all points in the form z and f of z, right? Come on. Lies in four-dimensional plane, that is 2 dimensions from the input of z and 2 dimensions from the output of w. Of course, a subset of four-dimensional space cannot be easily illustrated. Therefore, we come to a conclusion that we cannot draw a graph of the complex function. Now, if the point z0 is in the z-plane and corresponds to the point w0 in the w-plane, that is, if w0 equal to f of z0, then we say that f maps z0 onto w0, or equivalently, that is, z0 is mapped onto w0 by f. Notation S prime, if w equal to f of z is a complex mapping, and if S is a set of points in the z-plane, then for all the subset of images of the point in S under F, the image of S under F. I think there's something wrong with this. Sorry. This is image of S, right? And so the textbook reads, sorry, I can't read my handwriting. If W equal to f of z is a complex mapping, and if S is a set of points in the z-plane, then we call the set of images of the points in S under F the image of S under F, and we denote this set by the symbol S prime. Then S is called the pre-image of S prime. So what this is really saying in a geometric manner is that if we have the z-plane, right, that is x imaginary real, let's say this is the set. Draw a little bit bigger, right? This is the set S. Oh, that's not quite clear. This is S. And now if we want to apply this complex mapping, that is W equal to f of z, right? And now it maps into, or you may say transforms it into this shape, or some peculiar shape, really. Let's color it with red, and we call it S prime. And we say, well, maybe a different color, green. And we say points, maybe S naught, right, maps into, we call this W naught. Okay, like this. Now, moving on. Example 1. So now find the image of the half plane. Find image of the half plane real of z is greater than equal to 2, right? Under the complex mapping, W equal to IZ, right? And now, first I suppose we should illustrate the figures, perhaps over here. And you have the real axis greater than 2, inclusive, that is includes 2, greater than or equal to 2. And now consider the vertical boundary. So this is just x is equal to 2. Write 2 is over here, x and y. Right, for any point z on this line, well, we can do z is equal to, well, 2 plus I y, right? Y is unbounded, x is restricted to 2, and we know that, right, if y is unbounded, that's just, maybe we can write it in the bracket notation, right? Y is an element of this bracket, right? And now, if we would map this line, right, that is, well, f of z equal to I z, right? And now f of 2 plus I y, that is equal to I multiplied by 2 plus I y, well, that is negative y plus 2I, right? So now, if we take the real part of this, this becomes the imaginary axis. We can write w is equal to negative y plus 2I, right? And we know that y is not bounded, right? It contains y, right? And the vertical line becomes, well, now we're in the w plane, so maybe uv. So now, running out of space over there. So now you have uv. Oh, maybe over here. This is the z plane. This is the w plane. UV, like that. And, well, so the imaginary part of w is equal to I, right? That is, well, so we know 2I is over here, and we know it is inclusive, right? So we can draw like this. Right? And now we know that w is unbounded. No, negative y. Oh, sorry, y is unbounded, right? So what is y? Y is just the real axis. So you think of it like this: the real axis, real of w is equal to negative y, right? And y is unbounded. That means we can go from negative infinity to infinity. Well, where's the real axis though? The real axis of w is really just u, right? So u is equal to this thing. Well, that is equal to the negative y and the positive y, right? Like that. And, well, we say, now, perhaps I want to write it. Now follow the textbook. It says x is greater than equal to 2, right? And this is one of the constraints. I think we're finished, but still suggest to read the textbook. This is what the textbook says. And now if we but we skip a lot of steps over here, right? We just adjudicate on negative y and make assumptions based on that. But I say, well, if we don't know, I say we should plug in z is equal to x plus iy, right? And that implies I multiplied by x plus iy, that's equal to negative y plus ix. But we know that x is restricted, the smallest values x can get is negative. And now if we decompose this really, right, like this, so we know this f can be decomposed into uxy plus ivxy, right? And well, we can just read it over here, that is equal to negative y, and vxy is equal to x, right? And now so now we know that x is greater than or equal to 2, then that implies v is greater than or equal to 2. Well, where's v? So this is v, right? So we are correct there. And that just implies imaginary part of w is equal to, is greater than equal to 2, right? Now example 2, image of a line under w equal to z square. So that is w equal to z square, right? And we let c be the set of points on the interval on the vertical line x equal to 1, right? So now they define it as this. So what does that mean? Is that we define all the points on this line, right, for this equal to 1, 2, 3, like this, right? Perhaps blue, like this. And if equivalently, that is, you can write it in the complex plane, that is equal to 1 plus iy, for y is, this is y plane, so y goes from negative infinity to positive infinity, right? And now we how about we set wz, we've done this example already, but this is how you approach it. Let me redo it. We know z is equal to x plus iy, and that is equal to x plus iy square, and that gives us x square minus y square, right, plus 2x y I, right? I think this is what it was. And now we say our u is equal to x square minus y square, and v is equal to 2xy, right? And however, we know that our x is restricted to 1, and we know y runs between negative infinity to positive infinity, and we say, well, since x is restricted, we write like this, right? This is v. Well, that gives us 1 minus y squared, that gives us 2y, right? And now, but what is y? Perhaps we can write y in terms of x, right? So we know that v is equal to 2y, then y is equal to, well, we divide by 2 on both sides, that's v over 2, right? And now we know what y is, then we can solve for u, then u is equal to 1 minus v over 2 square. This is like how you solve for a Jacobian. I think this requires some linear transformation in calculus 3, if you will recall. Right, you solve for one of the variable and you substitute it into the other variable. And now if we say, how about right over here, now u is equal to, well, 1 minus v squared over 4. Alright. Well, now, how about we plot it like this? We know this is u, we know this is v, and this opens to negative, and we know it has the roots. That's when this is equal to 0, then v is equal to plus and minus 2, right? And now we know this is 1, so we know this starts from 1, and then you have this is 2, this is 2, this is negative 2, and well, let's sketch it. Then it looks like this. And this is the transformation. Right, so the parabola, we say this is equal to u of v is equal to 1 minus 1/4 of v squared. And now that is z after z. Well, that is z. Well, no, that is c under the transformation f of z equal to z squared. Now, definition: if x is equal to x of t and y is equal to y of t, and are real valued functions of of real variable t, then the set of c of all points in the form of x component is x, x component is y, and xy depends on t, where t is an element of where t goes between a and b, that is t goes between a and b, right? Called a parametric curve. It's called a parametric curve. The equations x is equal to x of t, y equals y of t for a between a and b is called a parametric equation of c. The parametric equation in the complex plane is defined as z of t is equal to x of t plus I y of t. Now, for example, consider the parametric equation x equals to cosine of t and y equal to sine of t, and t goes between 0 and 2 pi, right? And of a curve c, right? In xy plane, and that is a circle center at the origin, right, with a radius 1. Then the set of points z of t is equal to x component, that is cosine t plus I sine of t, right? And equivalently, t is also 2 pi, 0 to 2 pi, and describe the curve c in the complex plane. If we say t is equal to 0, well, what is it? That is z of 0 equal to cosine of 0 sine of 0, right? So this is our x and y component, really. And well, that is equal to 1 and 0, right? And that is z of 0 is equal to cosine of 0 sine of 0 plus sine of 0 and multiplied by I, that is equal to 1. 1 plus 0 I is equal to 1. So this is a basic, very rudimentary example, really. And now, definition. Parametric curves in the complex plane. If x of t and y of t are real valued functions of a real variable t, then the set C consisting of all points z of t equal to x of t plus I y of t from a to b is called the parametric curve, or the complex parametric curve. The complex valued function of the real variable t, that is z of t is equal to x of t, y of t, is called the parametrization of C. I think I spelled it incorrectly. I see, right? Parametrization. I must be in a hurry. Well, now. So if Z is any point on the line consisting Z0 and Z1, so, well, how about we draw this? We draw the grid, the axes, right? And now you have Z0 and you have Z1 over here. Well, we can draw as a vector like this, right? And we want to form a line segment like this, right? And this is the point Z. Okay. And, well, how do we write an equation for this? Well, we know that if we have, let's say, attempt, if you do z minus 0 well, it has to equal to t minus z1 minus z0, right? Why? Because, well, if you let it's really just z is one of the points over here, and these are the endpoints, right? I don't know if you remember calculus 1. I think calculus 1, it was you have a vector, right? That is the line segment, right? That is equal to v0, your initial point, right? And you want to scale it, right? How do you scale it? You want to find a vector like over here, right? So it's something like, I think it was t of 0 v0 naught, no, t of z1, no, v1 minus v0, right? So you have a vector and then you want to scale it. So you subtract, you get this vector, and then you want to add this number so you can scale it, right? Like that. So similarly, if you would add z0 over here, you get this one, this equation, right? I just happen to remember it. And now we say z of t is equal to z0 plus t of z1 minus z0, right? And what that is equal to, we can factor z0, really, right? So we can, how do we prove it? Well, that is, if you would distribute, right? So our claim is that we should end up with this function z0 1 minus t plus z1 t, and, well, really this is just, if you would distribute it, right? You can always factor out z0 if you group them together, right? You factor out z0, that this is 1 minus t, that is 1 minus t, and then you add z1 t. right? Like this. Fair. And we'll just end with this. Now, if you want to make it into, well, array, right? Oh no, just a line. What happened? Yeah. You will make it a line. Then you let y go from negative infinity to positive infinity. Right, oops, sorry. There should be t. Like this, right? Now, theorem. Common parametric curves in the complex plane. So the parametrization of the line containing the points z0 and z1 is, well, the formula we just derived, right? That is a line. So this is an illustration of it. You can go from negative infinity and you go from positive infinity, right? Now, line segment. Well, simply you can just let it go from 0 and 1, right? So if you set this equal to 0, then you get z0, and what's plus 0? That is just z0, right? And if you would set this equal to 1, then 1 minus 1, that is equal to 0. You have z1, so z1's over here, right? That is correct. So this is an illustration of a line segment. That is for t go from 0 to 1 inclusive, right? And if you want to find an array, that is something like this. This is an array starting from z0 to infinity. Well, you can just make it go from 0 to infinity, right? And now, if you want to go from a circle, we know that how do we make a circle? Well, it can be modeled by this formula. So you have a z0. First you add to the point, and then you want to make this into, what's happening? Right, you want to make this into a circle, right? So as t spans from 0 to 2 pi. Really, this is just the polar form, if you will recognize it. So this is basically z1, right? And now, how about we write the polar form in the exponential form, right? So I think it's very straightforward. And well, now, for example, restricting the values of the parameter t, okay, for these two, well, setting z0 equal to 0 and r equal to 1, right? Well, you should expect a circle, right? This is z0 is equal to 0 and radius 1. So you expect something like this, right? Right, we see if we write it in terms of, let's say I would go over here. This becomes, what is r? R is 1, right? And then multiply by t, right? So really just t plus 0 like this, but this is enough, right? And the parametrization, that is the parametrization of the semicircle arc of the unit circle contained at the origin of the plane, or that is 0 plus 1 EIT, right? And if you go from 0 to pi, right, there's a semicircle, and then you go from pi to 2 pi, like this, right? And now, let's move on to equation 6. This is a very short one. W equal to IZ, right? And C is the line of x equals to 2, right? If you would recall, you have right, like this, and given by z of t equal to 2 plus it. Well, how do we model this, right? We know 2, this is over here, right? 2 plus it, and we know I is just implies on the the imaginary axis, and we want it to go from negative infinity to positive infinity, right? So, well, we can set it equal to, we can set the boundaries in negative infinity to infinity, right? And f of z is equal to it is this point. So how about we say, well, w is equal to iz, that's equal to f of z, and we know z is equal to 2 plus it, f of 2 plus it is equal to I times 2 plus it. Well, that gives us negative t plus 2I, right? And we know that t goes from negative infinity to positive infinity, right? So now that is the parameterization of C prime, right? So really it's just, if you would map it, right, and you go from, well, if that is, if you u, v, right, restricted, that is 2I, that's over here, and we know this is negative t to positive t, so that is this line, but that is equal to 2t or something. No, this is v equals to 2 there. Image of a parametric curve under a complex mapping. If w equal to f of z is a complex mapping, and if c is a curve parameterized by z of t from a to b, then w of t is equal to f of z of t from a to b. Is a parameterization of image c prime of c under w equal to f of z. So you make a substitution, you put it in, right, very straightforward. And now we want to find image of a parametric curve, right? So now if we would let w equal to I of z, take the complex conjugate of it. So now we know that f of z is equal to iz complex conjugate, right? And let c denote the segment. So now we want to, well, c is given, so let's draw over here. This is I, and this is 1, this is c, right? But how do we find this segment? Well, how about we pick, really, 1 to 0, so we know that z naught is equal to 1, 0, right? And we know that z1 is equal to 0, 1, then we say z of t is equal to, well, z naught, that's 1, 0, plus z naught, and then you scale it. 1 plus 0, 1 minus t, right? 1 minus t. Is it? Oh, right. 1 minus t plus z1 is 0, 1 t, right? Well, we say w of t is equal to f of z of t, right? We just found out what z is. That is equal to, if we would take the complex conjugate of really just 1 minus t plus it. Well, really, this is just multiplied by 1, right? So that is 1 minus t, and then you have plus t like this. But this is I, so you have to remember to add an I over here, and you take the complex conjugate, right? So that is equal to negative I. You flip all the signs of I, right? So that is when you distribute it, right? You multiply out, but this gives negative No, the complex conjugate applies on I, that gives a negative, right? And you have 1 minus t, right? And then I and I, that is negative 1, right? So the complex conjugate does not apply to it, and we know t go from 0 to 1, right? From a line equation, right? And now with the identification of, and now if we would identify your z0, well, your z0 is equal to your negative I, right? Look over here. Negative I and your, maybe we say prime, right? And then z1 prime is equal to negative 1. Therefore, we'll c prime, alright, goes from negative I to 1, right? So now we say, well, that is c1, now we want to find c prime. So this is negative I, this is 1. And this is c prime. And recall that this is c1, right, from 1 to I. And then we say this is f of z, right? Now, example 4. Find the image of a semicircle shown in color in figure 2.6. So, well, let's draw it now. Well, forgive my lack of artistic aptitude. This is the best I can do. This is negative 4i. This is 4. Oh, I already wrote 4, so this is redundant. Now, this is negative 4, right? But we want to find a semicircle, right? That is this one. So it goes from 2, right? This is called C. This is 2i and negative 2, right? And now, under the complex mapping W z square. Well, it's hard to imagine how we can map this semicircle into a full circle and it enlarges it. Well, but if we look at the mapping over here, it's a square, so I think it automatically fills up for the other half because it's mirrored, it's squared, right? And that's just the nature of square. And now we know that f of z given by this clue is just z square, right? And now we know that well, z naught is equal to 2, right? And we know our r is 2, right? Goes to negative 2. Sorry, this might look like a negative 1 to you, but this is a negative 2. Now this looks like a 2, maybe like this, negative 2, right? And now recall our formula up here, right? It's just this, really, but because it goes from, it's a semicircle, I think it goes from 0 to pi, right? So now we can write this in, we can write it in polar form, or we can write it in exponential form, right? How about we write it in exponential form? We go from 0 to pi, right? And now this is our z of t, right? This is our z of t is equal to 2eit, and we know our wt, that is equal to f of z of t. there, and that is equal to, if we would write z over here, replace it with z, and then square it, right? And that gives us 4 squared, that's 2 squared, that's 4, and then we multiply it, that is 2it, right? And it still goes from 0 to pi. And now, if we would set, how about t is equal to 1/2 s, right? Well, if we make the substitution, we can cancel out the 2, right? And it makes this into 2 pi. So I think that it makes into something that we desire, right? It transforms the equation into a more desirable situation. Well, that is w of s, now it's capitalized w, that is equal to, well, 4e to the is from 0s to pi, right? And now we see this really maps it into the whole circle, right? Radius 4, and then goes from 2 pi, that makes it a full circle. Well, how about we complete it by saying, we know z0 is 0, r is equal to 4, therefore circle of radius 4, and we know the modulus of w is equal to 4, right? So it represents the circle, right? Because, well, this can be really just written as modulus of w is equal to 4, right? That is really just saying all of the points such that modulus of 4. So this is the definition for the circle of this. Right. Now we can use computer. What is this? Use of computer. I've forgotten W. It says use computer, so I was confused. Use of computer. So we can use Maple, Mathematica, or Maple. Is it Maples or Maple? I see Maple. This is this meant to be a comma. Maple and Mathematica are useful computing tools, and in Mathematica, a complex function may be defined by f of z, and then you have underscore, and then this is colon equal to an expression in z, and then similarly for g, but I think I wrote something wrong. That is really just t dash, right? An expression in t, right? And it follows, if we want to find w of t, well, we can just plug in g of t into the f of t, right? But it uses these medium brackets, right? In Mathematica, plots the graph with the command parametric plot, then bracket, more bracket, right in definition, real of wt, imaginary wt, right? Right, and then there's this bracket over here, close bracket, right? And then comma tab, right, in the bracket, and this is 2.2.